anything, you can talk to me. This is red. It's not good. Okay, let's start. So today we start a new chapter of our lives. If you are looking at the book that I said is recommended but not required, that would be chapter 9. It's called the Laplace transform. So you might think yet another transform, but this is actually very closely related to the Fourier transform. Okay, so you're not going to be surprised by anything you see. It's called the Laplace transform. All right, so, the reason Laplace was another French guy, but the reason he's given credit for this is not because he really did the types of things we're going to do in this course, but he had done some things that are vaguely related, and people gave him credit at the end. Next time I'll tell you a little more about the history of this. So, what is the Laplace transform? So, Fourier transform, you remember, I hope you do. So I give you a signal, and you give me the alternative representation of this signal by taking this integral when it exists, right? And we call that x of omega. I also said that sometimes I'm going to write this as a function of j omega. And today you'll kind of understand why. Okay? And Laplace transform is closely related. So what you do is you take the integral again, x of t, but this time you multiply it with e to the negative s times t, and s here is a complex number. Okay, so unlike the Fourier transform, where we have a function of one real variable omega, we now have a function x of s that's a function of a complex variable s. All right? So when we say it's a function of a complex variable, that really means it's a function of two things, right? The real part and the imaginary part. So it really is a function of two variables. All right. So when you look at these two expressions, they look alike. And you should see a way to recover the Fourier transform from the Laplace transform. What would you do? Yeah, just substitute s equals, just drop the real part. S as a real part and imaginary part. If I choose s to be j omega, which means it's purely imaginary, then you're going to get x of j omega, right? So in that sense, Laplace has a little more information than Fourier transform, right? If I have the Laplace transform already, I can just substitute in place of the complex number s, j omega, and I recover the Fourier transform. Okay, so Laplace has more because it's a function of two variables, the real part and the imaginary part. You drop the real part, you get the Fourier transform. Now, I claim that this is not the first time you're seeing this in this course. Let's see anybody can remember an appearance of an integral of this form. In fact, with s, where s was a complex number. Let's check your memory. What? One over 8 plus j omega. That was the Fourier transform, though. Transfer functions, yes, that's the answer I was looking for. So that was, I think, back in lecture 3. So we said that, at that point, we had not seen Fourier transform, nothing, right? We had just talked about linearity, time invariance, and all that. We had just learned about convolution. Just using convolution, we said that if I give you an LTI system, and if you apply the input e to the st, if the impulse response is h of t, so this is an LTI system, right? LTI. What comes out is h of s, the scaling factor, times e to the st. So we said e to the st is like an eigenfunction, you could say, right? So because when you put that in, it comes out intact, just like eigenvectors, right? A matrix multiplying an eigenvector returns the same eigenvector without changing it, right? It just multiplies it by a factor, which is called the eigen value. Okay? So in that sense, e to the st is like an eigenfunction. Okay? All right, so, and we said there that h of s is defined as follows. Take h of t, multiply with e to the negative st, integrate over t. So that really was the Laplace transform of the impulse response. Okay? So now we connect things. Therefore, the transfer function h of s is the Laplace transform of the impulse response h of t. Just like the frequency response was the Fourier transform of h of t. Okay? And just like that, if I have the transfer function, and if I put s equals j omega, of course I recover the Fourier transform, which is the frequency response. Okay, so this is the transfer function, or the book I think calls it the system function, and this is the frequency response. Okay, so that's the difference. Laplace is a little more general in the sense that I can recover Fourier from Laplace, and this is the context where it emerged in lecture 3. It was the transfer function of the system, where we showed e to the st was an eigenfunction. All right, any questions? This is a quick introduction and a quick review of things we studied already. Do you know where the word eigen vector comes from? You heard that, I guess. Somebody said German. It means really self, right? Self value, self vector. Because those are inherent to the matrix or system, whatever it is. And somebody, when translating it to English, thought that this eigen must be a professor of some sort. So they translated it as eigenfunction instead of calling it the self function. Anyway, that's an aside. All right, so let's look at some examples. Do you have any questions? This is pretty easy, at least the way we defined it. All right, so we'll have a few examples, and you'll see the similarity to Fourier transforms, or you also get to see the differences. So example 1, I'm going to enumerate these examples because I'll keep referring to them. All right, so the first example will be something we discussed as our first example also for Fourier transforms. Something that is exponentially decaying. I'll take a positive so it actually decays, multiplied with the unit step. Okay? So, how would I find x of s, big X of s, to Laplace transform? I would have to integrate by definition, right? This time from 0 because u doesn't start until time equal to 0, right? E to the negative at and times e to the negative st, right? dt. What? You can't see it. Oh, okay. That's why some of you are smiling. It's more helpful if you tell me what's going on. Okay, so All right. So S, remember, is a complex number, so you can just write S equals real part. I'm going to call it sigma. Okay, why not? The real part, I'm going to call it sigma. And the imaginary part, I'm going to call omega, just to be consistent with the Fourier transform, right? So therefore, what we're looking at, I could do this integral, okay? It's not a big deal, but I want to show you the connection to Fourier transforms. So I'm going to substitute in place of S, the real part, plus J times omega. So I'm going to get e to the A negative AT, e to the negative sigma t, and e to the negative J omega t dt, right? 0 to infinity. I'm writing it in this form by splitting S into its real and imaginary parts, because that way it kind of looks like the Fourier transform, right? The Fourier transform of what, though? Not e to the negative AT, but e to the negative AT times e to the negative sigma t. Right? So this looks just like the Fourier transform of e to the negative a plus sigma t. Right? And what is the Fourier transform of e to the negative a plus sigma t? Okay, let me first remind you of the Fourier transform of this guy, right? The Fourier transform of that, now you have less of an excuse not to remember. 1 over a plus j omega, okay? So the only reason I'm doing it this way by writing real plus imaginary parts is because I want to make it look like a Fourier transform, so you can just scream and tell me the result, since you're so professional with Fourier transforms. So what is that? Instead of a, now I have a plus sigma, right? Just change this a to a plus sigma, and you're going to get a plus sigma plus j omega, right? So that's it. But then this should be a function of s. So let's identify an s hiding in this expression. Well, that shouldn't be hard. So where's this? It's here, right? So this is s. So this is s, right? So we have 1 over s plus a. Okay? So when you told me the Fourier transform is 1 over a plus sigma plus j omega, you made an assumption that you didn't tell me about. I tell you about my assumptions. It's not fair when you don't tell me about your assumptions, right? I here said if a is positive, because otherwise that integral is not going to converge. Right? And your integral here will converge if a plus sigma is positive, right? So we can claim that this is the Laplace transform x of s, provided that a plus sigma is positive, meaning that, remember this is the real part of s, right? Meaning that the real part of s is bigger than negative a, right? So when you say this integral gives me that, you need to be clear about when that integral actually converges, when that's a well-defined object. Wait, did I do this right? No, it has to be positive. So what am I doing wrong? Oh, less than negative a. Yes. Duh. Okay. Does that make sense? Yeah, this is wrong. The first one is wrong too. Is that what you're saying? What's going on? So wait, here we said a positive. Now we're saying a plus sigma. What's wrong with that? A plus sigma should be positive, right? You're scaring me. So real part is bigger than negative a. That's right. Okay. Is that true? Yes. Of course. Yeah, I was correct in the first place. Okay. So, all right. So, okay, we gave the answer here. So, for this x of t, e to the negative at u of t, we found the Laplace transform to be capital X of s 1 over s plus a. Do not forget this example because this is the first example. Usually that means the simplest example, right? So, you know, you'll see quite a few functions and their Laplace transforms, and this is one of them that you'll see over and over and over. You might as well remember it the first time. And but then when we specify the Laplace transform, we also specify what kind of s we are talking about. Under what assumptions on s does that integral convergence give us this? And that is what we found. The real part of s in this example must be bigger than negative a, right? So that's the answer. So what I just wrote here, the condition on s, right, specifying for what s the integral converges, this is called the region of convergence. We're going to abbreviate this as ROC, all right, region of convergence. That means what is the set of complex number s for which what you just told me makes sense, the integral converges, right? And in this case, it has to be such that if I look at the complex plane, the s plane, the real part is sigma, the imaginary part is omega, right? The set of complex variables s for which the convergence happens is when the real part, sigma, is bigger than negative a. And let's say a is a positive number, so negative a is a negative number, right? In that case, the region of convergence is to the right of this dashed line. And the dashed line does not include, I mean, the shaded region, despite my poor drawing, should not include the dashed line. I'm trying to do a little touch-up so that doesn't happen. Okay. All right? So that's the region of convergence. So there's a big difference here from the Fourier transform, right? Fourier transforms, the integral either converges or it doesn't, right? We don't negotiate. Fourier transform is very stubborn. Laplace transform is more flexible. It says, okay, I will converge if my real part is bigger than such and such, right? It's more malleable in that sense, right? So for Fourier transforms, we don't have region of convergence. Yes or no is the answer, right? For Laplace transforms, we have an extra knob. That's the real part of s, which didn't exist in Fourier transforms. And we can tune that until the product of our signal with e to the negative st starts decaying exponentially so that the integral converges. Right? That's the idea of the region of convergence. Right? I do not intend to make a big deal of region of convergence in this course, but we need to be aware that it is an integral part of Laplace transform if you're talking about Laplace transforms. If you look at the book, Chapter 9 is where Laplace transforms are discussed. It makes a much bigger deal of the region of convergence. I used to follow the book years ago, but I've become older and wiser, and I decided to drop further discussions of region of convergence. It's kind of good to know there is such a concept and it's relevant, but it is not the most important part of Laplace transforms. When you know why Laplace transforms are useful, and that will sort of come in the next lecture. Today you'll have to bear with me and assume that what I'm telling you is useful. All right, so that was example 1. And example 2 is going to be kind of similar, although it will be now a right-sided signal. All right, why am I putting all these negative signs to torture you, right? It's a little silly, but we'll see what's happening. So now I'm going to work on the Laplace transform of this. In the first example, I made the Laplace integral look like a Fourier integral, and we used what we already knew, right? In this example, I could totally do the same thing with some changes of variables, but I'm not going to do that. I want to just illustrate how we actually do Laplace transforms. So we have to take this integral from negative infinity to positive infinity, but it will stop at 0. And the reason is u of negative t is a left-sided step. At time equal to 0, it ends. So no need to integrate any further. And then I'm going to get a negative sign because this is negative. And I'm going to have e to the negative at, e to the negative st, dt, right? All right, so what I'm going to do next is I will replace I will define a new time variable, negative t, so that what I'm integrating looks like a plus s tau. So I get rid of these negative signs here. Does that make sense? Okay? But what happens to dt then? It becomes negative d tau, right? Also, the limits of the integration will change, because this here meant t is equal to negative infinity, but that's really is now tau equal to positive infinity, right? So that's going to be positive infinity, and 0 stays at 0. And we have the negative sign, which we carry over from here. Okay, so the negative signs happily cancel. So we get infinity to 0 e to the a plus s tau d tau, right? But it's funny to start from infinity and integrate backwards, so I'm going to switch it back to 0 to infinity, and that will introduce the negative sign that was had just become positive, right? So too many negative signs going on here, but that's it. All right? So what is the integral of e to the something times tau? It's itself divided by that something, the factor in the exponent, right? A plus s tau. Right? And we have a negative sign. And then the limits of integration are infinity and 0. So what happens at infinity? That really depends on what e to the a plus s tau looks like. So when can you say this is actually 0? If the real part is negative, we don't care about the imaginary part, because the real part is an envelope, right? If that decays to 0, that's fine. You know, it's going to 0 anyway. It can wiggle while it's going to 0. It can whimper, to quote the president, but it will go to 0, right? But so what really matters is, so for me to be able to eliminate what's happening at infinity and say 0, I need to assume that the real part of a plus s is negative. So under that condition, the value at infinity is 0. And then I subtract the value at 0, but then there was already a negative sign, so that becomes plus again. But anyway, what matters is that we're looking at a plus s tau when tau is equal to 0. So this term becomes equal to 1. So we get 1 over s plus a. Okay, so that should be slightly surprising, because example 1 wasn't quite this signal. Nevertheless, it gave us the same Laplace transform, x of s, 1 over s plus a, right? So how come two very different signals are giving me the same result? How can I distinguish between those two if their Laplace transforms are the same? Any ideas? Region of convergence is what differentiates them, right? So in example 1, the region of convergence was this, right? Real part of s had to be bigger than negative a. In this example, the region of convergence is hidden here. And what it really means is that ROC is real part of s. We assume a is real, right? So the real part of s is going to be negative, less than negative a, right? It really is the complement of the region of convergence of the other example. So now it's to the left of this line. Okay? So like I said, I'm not going to make a huge deal out of regions of convergence, but it is good to know that signals that are right-sided, signals that start at a certain time and go towards infinity, are associated with regions of convergence that are also right-sided. Okay? Whereas signals like this one, that already end at time equal to 0, right? This is t, and before that it's going to look like an exponentially decaying thing. Or actually, I'm sorry, well, anyway, A can be anything. It can be decaying. It can be like this also, right? In any event, because it's a left-sided signal, the region of convergence is also the left part of the plane, starting at a certain point, negative A in this case, right? So that's sort of a differentiator between right-sided and left-sided signals, although they can give you the same X of S. All right, so if we compare what we found here to Fourier transforms, what can you say? How will I get the Fourier transform of this signal out of the Laplace transform? The trick is you substitute S equals j omega, right? So again, it becomes 1 over j omega plus A. But now the question you have to ask yourself is the Fourier transform going to converge? Is the Fourier integral going to converge, right? How can I give the answer to that question looking at the region of convergence of the Laplace transform? So, okay, so let me be a little more clear. Yes, you're right. But so the main observation is if we write our Laplace variable S, which is complex, as real plus j omega, right? Then the Laplace transform, I'm going to use this fancy cursive L for Laplace transform of the signal X. I told you in one of the first lectures, when you're referring to a signal, don't say x of t, because x of t is the value of the signal at time t, but I'm going to go against my advice now, okay? So I should really say L of x, but that will, sticking to my own advice would require writing a couple of more lines, which I don't want to, okay? So the Laplace transform x of t, as we saw in example 1 back here, is the same thing as the Fourier transform of e to the negative sigma t x of t, right? So the only thing that the Laplace does is it gives us this real part that you can use as a negotiating bit for the Fourier transform to converge. That's one way to think about it, right? All right. So if the region of convergence, if the ROC of x of s includes sigma equal to 0, right? That means the Fourier integral itself converges, because then this e to the negative sigma t term is just 1, right? Then x of t has a well-defined Fourier transform. Okay? So in terms of regions of convergence, that simply means you want to make sure that sigma equal to 0. Sigma is the real part, right? Real part equal to 0 means the line that's the imaginary axis, right? If the imaginary axis is part of the region of convergence of the Laplace transform, that means the Fourier transform exists, right? If I go back to these two examples then, in this case, if negative A is actually positive, meaning that A is negative, then the imaginary axis is inside the ROC. Therefore, the Fourier transform would also be well defined. And you can say then the Fourier transform is 1 over A plus j omega. In example 1, which is the right-sided signal, if A is strictly positive, the imaginary axis is part of the ROC. And in that case, we know already that the Fourier transform exists. It's this, which you can recover by substituting S equals j omega. All right? So, to summarize, the important part is you can recover Fourier transforms from Laplace transforms by substituting S equals to j omega, but that substitution makes sense if the j omega axis, the imaginary axis, is part of the region of convergence. Otherwise, you're talking about an integral that doesn't converge. All right? So, do you remember any kind of useful signals for which the Fourier transform sadly did not really converge? I want to make sure that's one of my examples. It's not, but well, so this is still actually example 1, special case. Example 1 was e to the negative at ut, right? If I set a to be 0, what do I get? U of t, right? Did we have a Fourier transform for u of t? You're integrating e to the negative j omega t, which doesn't decay, right? Good luck. It's not going to converge. Whereas, we do have an answer for the Laplace transform already. It's 1 over s plus a, right? X of s. So when x of t is the unit step, x of s is 1 over s plus a being 0 is 1 over s, right? So we do have a Laplace transform. What is the region of convergence? The real part of s must be strictly greater than 0, right? So this is the ROC. Real part, imaginary part, and then the ROC is to the right of the imaginary axis, right? Is the imaginary axis itself part of it? No, we said strictly positive, right? So therefore, I'm going to dash this line, okay? Because that's not in there. That's just a boundary, but it doesn't belong in there, right? So what can I say about the Fourier transform? Fourier transform does not exist for this example because the imaginary axis is not an element of the ROC. It's the boundary, but the boundary is not part of it. Okay? So that's why we didn't have a Fourier transform, but now we happily have a Laplace transform here. Only because that this real part sigma helped us, right? If I put sigma positive, I'm going to get e to the negative sigma t times u of t, which now converges, right? So Laplace, in a sense, overcomes these convergence issues by giving us this sigma, a knob that makes things converge, right? So it's kind of useful, and we'll see how it's useful in dealing with LTI systems in the next lecture, which essentially means solving linear constant coefficient differential equations. Laplace transforms are extremely useful for that. You may have taken 54 or whatever. Have you taken a course where you were given linear constant coefficient differential equations? Was that 50-something, 4, 3? 54. So there are all these weird things, right? You find the homogeneous part, you find the particular solution, add them up, substitute the initial conditions, etc. All of these become trivial algebraic manipulations that requires no specific tricks for homogeneous, particular, etc. when we use Laplace transforms. And you'll get to see that in the next lecture. And that's all with the help of Laplace transforms. And the guy who actually made all these discoveries was a guy by the name Heaviside, who had no math degree, in fact, no degree. He was a self-educated or self-taught electrical engineer 100 years ago. And he introduced all these things, unit steps, delta functions, not quite rigorously, but he had the right ideas. Basically, this course is based on his ideas, really. And he was no mathematician. He was, in fact, ridiculed by mathematicians. But anyway, but while you're here, you might as well learn the math and be able to back up your intuitions and ideas with the solid math, right? That's what we expect from you. All right, so where am I? Okay, I didn't go very far, did I? I'm still at example 2. But anyway, we did some useful things. Let's look at another example. This is really example 1 twice. I mean, two signals added, both of which conform to what we had in example 1. Negative e to negative t, u of t. All right. So what's the Laplace transform? Don't make me do this again. Sum of the Laplace transform. So what can you say about the first one? 3 stays, it's just a factor, right? S plus 2, because this 2 is like our A in example 1. And now you get 2 S plus 1. And you're done. Well, you're not quite done. It's nicer to simplify this a little bit, which you do by making them have the same denominator. So, and we can do this by doing these simple manipulations. S plus 2, S plus 1. And the numerator becomes S minus 1, right? Is that correct? All right. What is the ROC? For the first part to converge, we need real part of S to be bigger than negative 2. And for this, we need bigger than negative 1. I need both because I have both terms. So the more restrictive of the two is this one, right? So that is the ROC of the whole thing. Right? Example 4 looks just like example 1, but not quite. Now I'm going to write e to the negative, instead of a, I'm going to just say alpha t, u of t, and you might be wondering what's so different. You just called a alpha. Well, the difference is that I'm going to allow alpha to be a complex number, right? Why not? So what can I now say about the Laplace transform? It really is the same derivations, right? So, again, you're looking at, the integral from 0 to infinity, e to the alpha plus s t dt, right? And it's going to give you 1 over s plus alpha, as we discussed in one of the previous examples, provided that e to the negative alpha plus st is going to 0. And the part that decides whether that's going to 0 or not is the real part. The imaginary part just jumps up and down. It doesn't add any value, right? The convergence is determined by the envelope, and that comes from the real part. So we want the real part, so that is the case, if the real part of s plus alpha is positive. So s and alpha are both complex numbers. If I add two complex numbers, the real part of the addition is the addition of the real parts, right? You can naturally separate them. So that simply means that the real part of s needs to be bigger than negative the real part of alpha. And of course, if alpha is real, call it a, then we're back to example 1, and the real part of is itself, so the real part of s must be bigger than negative a. Same thing. We recovered the same thing, we just generalize it, right? So why is this generalization useful? Now you'll appreciate that, because I'm going to be able to revisit a signal that was that is commonly used, but again, sadly, it did not have a good, well-defined Fourier transform unless we want to introduce these distributions, whatnot, right? And that is the sinusoidal. So that's example 5. That will be enabled by example 4, where we allowed alpha to be complex. So I'm going to take, hang on. I'm obsessing about my notation, okay. All right. Anyway, so I'm going to look at x of t cosine omega naught t for some omega naught times u of t. Okay? That doesn't obviously converge exponentially, so we did not allow any Fourier transforms for this before, except when we said, well, Fourier transforms can be generalized using distributions, then you'll have a spike, a delta at omega equals omega 0 and all that. But let's not worry about that now. So let's just talk about the Laplace transform. Okay, so how can we leverage example 4 to find the Laplace transform of cosine? Because it's not going to look pretty if you just write this, multiply it with e to the negative st, try to integrate. It's not nice, right? But example 5 has done all of these nasty integrations, so you might as well use it. So how can I bring in the result of example 4 to example 5? What should I do in example 5? The usual trick, right? Write your cosine as e to the j omega naught t plus 1 half e to negative j omega naught t, right? Okay, so now everything is easy because we already did this example, only this was alpha, right? And this was alpha, right? So using example 4 twice, I can say that the Laplace transform of the first component is 1 half 1 over s blank. Let's wake up. It was s. Oh, actually, I'm sorry. This is negative alpha, right? To be consistent with example 1, because we had e to negative alpha t. So this is negative. Okay, now tell me. It would be s plus alpha from example 4, but alpha is negative j omega, so j omega is 0, right? And for the second part, I'll have s plus, because alpha is now positive j omega naught, right? Okay, so if that doesn't look pretty to you, it can be prettified. So you're going to get the sum of these two, and then in the denominator you multiply the two. S plus j omega naught. Okay. Why am I doing this? I don't need this. Okay, so stuff cancels. This and this cancel, which is good. And then actually the 2s here will cancel with this 2, so that's also good. So what happens in the denominator, though? Can you just look at that very special form of the denominator and say, that's just blah. S square omega naught square, right? Something like s minus b times s plus b is s square minus b square, right? In this case, b is j omega naught. Its square is negative omega naught square. So negatives cancel, you get positive. All right, and then 2's cancel. So the good news is that the answer is simple. X of s for a cosine starting at time equal to 0 is s by s square plus omega naught square. And when does this converge? Does it converge for the imaginary axis when the real part of s is 0? No, because that would have been the Fourier transform, right? But it does converge when the answer will come from example 4, right? Because we said we said the real part of s, I thought I was highlighting, not erasing. Negative real part of a, right? Alpha. Okay, so, but alpha in this case is just j omega, right? So the real part of that is 0, so we just need the real part of s to be positive. So now I'm going to really highlight. So this was my signal. This is the Laplace transform. The region of convergence excludes the imaginary axis, therefore no Fourier transform existed in the strict sense, but the Laplace transform does with this region of convergence. Something similar, I'm not going to repeat. Yeah. Geometric interpretation of what? You want to draw what? There is sort of a geometric interpretation of it, and it will come in 15 minutes. I mean, not exactly, because we're going to talk about the so-called poles and zeros of the Laplace transforms. Those are just the roots of the numerator and denominator. So we're going to mark them on the complex plane, and then later we'll have some geometric interpretations of the frequency response and things of that sort. There'll be some kind of geometry coming from this nicer form of x of s. Okay, whether it satisfies you or not, I don't know, but it will come. So we can do similar things for sine omega naught t times u of t, which I'm not going to do, but I'm going to tell you the result. The Laplace transform will be, it will have the same denominator, in fact. Okay? But in the numerator, we're no longer going to have this s. We'll just have omega naught itself, without a square or anything, just omega naught. Okay? And again, the same region of convergence. All right, one more example, and then I'll give you a short break. This example is actually a simple continuation of the last one, where we had cosine. Now we're going to look at x of t equals e to the negative at times cosine omega naught t times u of t. All right, now we have an exponential factor. Cosine, let's imagine a being positive, right? Cosine keeps oscillating, but we have now given it an envelope that decays if a is positive, or it grows if a is negative. So that will, of course, change the nature of things a little bit. But again, the ideas are very similar. So I write, as always, this to be e to the j omega naught t plus 1 half e to negative j omega naught t. But then a adds on top of that, right? So I have 1 over 2 e to negative a minus j omega naught t and a plus j omega naught t. Okay? So now I apply example 4 twice with these two different values of alpha. So this is my alpha and this is my other alpha, right? For the first case, I'm going to get 1 over s plus alpha minus j omega naught. And for the other one, I'm going to get 1 over s minus alpha s plus a. No, a, right? Why am I writing alpha? A. S plus a. This is again a, right? Plus j omega naught. So that's basically it. But that you can simplify it. And when you simplify it the way we did it, I'm not going to repeat it, is you're going to get s plus a in the numerator instead of s. And you're going to get s plus a squared plus omega naught squared. And the region of convergence now will become, I need your guesses. What is the real part of alpha in both cases? Real part of alpha is a. So therefore I need real part of s to be bigger than negative a. Right? So that means if a is positive, then the ROC is going to look like this. It's going to be to the right of this line, which means that it does include the imaginary axis. Okay? So the conclusion is if A is positive, this actually does have a Fourier transform as well. And how would I get the Fourier transform? The Fourier transform exists. All I have to do is substitute in the Laplace transform S equals j omega, right? J omega plus a, j omega plus a squared plus omega naught squared. You can further simplify this. Of course, you'll get a negative omega squared. So you can do the math, but you know, the point is that the Fourier transform exists, and you can recover it by substituting S equals j omega. All right, let's take a short break and relax. break short, okay? And I'll jump over some details. That's my resilience. How is that? We'll go faster. Do everything in this hour. Who knows if we have power on Thursday or not? All right. So, okay. So, what are poles and zeros? This is a term that you're going to keep hearing today until the end of the semester. And if you take 123, you'll hear even more of those, or 128 of Laplace transforms. All right. So, let's assume. Suppose x of s is rational, is a rational function. What that means is it's a polynomial divided by a polynomial. So it's a numerator polynomial. I'm going to call it n of s, n for numerator, divided by d of s, denominator. Right? They are both polynomials. Right? So if our Laplace transform has that form, then we define the poles of x of s to be the roots of the denominator polynomial. Okay, what that means is, of course, those complex numbers s for which d of s is equal to 0. Okay, and then the zeros of x of s are the roots of the numerator. Okay, so zeros are easier to interpret because they are really zeros, right? If you take that s, right, when the numerator becomes 0, the whole x is 0, so the word 0 makes sense. Pole is when the denominator becomes 0, therefore x actually explodes. And because of that, in fact, for those values of s, you can't possibly be in the region of convergence. Clearly, you haven't converged anywhere if you're getting infinity when you substitute that particular s, right? So let's look at a couple of examples. Example 3 was, I can't even keep track of these examples, but example 3 was this, right? Here. This was our x of s. So where is the 0? Okay, at 1. So what we usually do is we make a sketch of the complex plane, real part versus imaginary part, and put a 0, some circle that looks like a 0 where the 0 is, and that is going to be here at 1, right? For poles, we put these cross types of things. But first tell me where the poles are. -1, and that's the sign we use for a pole. And there's another one at -2. Okay? So that's we have 1, 0, and 2 poles. And the region of convergence is to the right of the vertical line with real part equal to -1. So as you can see, the pole actually, neither pole is inside the region of convergence. They just can't be because the value is infinity. That doesn't look like convergence of the integral. All right, so we could do other examples, but I'm not going to do all of them. Let's look at this example 5. Let's make a little drawing here of the complex plane, and you tell me where the poles and zeros are. The 0 is easy. It's at 0, okay. Doesn't get easier than that. And the poles, when is the denominator equal to 0? So the roots of the denominator are when s is plus and minus j omega naught, right? So here and here. So there you go. You have 2 poles and 1 0. And we found in this example that the ROC was the right half plane. And the imaginary axis is the boundary for that. So clearly, again, the poles are on the boundary but not inside. All right, no need for further examples. Let's look at one last example before we move on. That will be example 7. This time we have the delta appearing. Maybe while I'm writing this, think about what would be the Laplace transform of the delta function, the Dirac delta. Just apply the definition and you'll see a very easy answer comes up. Okay, what is the Laplace transform of delta? It's 1, because delta times e to the negative st integrated is going to pick out the value of e to the st when t is 0. And that's 1. And what is the region of convergence? Anything goes, because s doesn't even matter. You're just looking at e to the st when t is equal to 0. Who cares what s is? The convergence is a non-issue. Okay, so that will give us 1 for any s complex. Now this part is going to give us, you should be able to tell this to me now instantly. 1 over s plus 1, right? And the real part of s has to be bigger than negative 1. And this, let's include 1 over 3, of course. This is 1 over 3 s minus 2. And the real part of s should be bigger than 2, right? Okay, so of course, you have to make all of them happy. The first is happy anyway for any s. But you need the intersection of these, right? So which one encompasses the other? This one, right? So these are bigger, so when you look at the intersection, this will come out. Okay? And then you can, of course, add these terms to find the Laplace transform, and when you simplify it, which I'm not going to do here, you will get s minus 1 squared after a bunch of simplifications. All you're doing is you're adding 1 plus this and simplifying, okay? And I trust you can do that. I'm not going to do it here. S minus 1 squared s plus 1 times s minus 2, okay? And the ROC is when the real part exceeds 2. So let's make a sketch of poles and zeros and move on from this discussion of poles and zeros, because trust me, you'll see a lot of poles and zeros going forward. You don't need to spend too much time. So where are they? Zero at 2. No, 1. Just testing you. And I have 2 of them, right? So they're at the same location, but I'm going to put them a little apart so you see that there are 2 of them. And then the poles are at negative 1 and at 2. And the ROC is to the right of 2. So once again, the pole is not in there. It's on the boundary. Okay, so much for ROC and poles and zeros. Now I'm going to tell you about the going back. So when we did Fourier transforms, we did also the inverse Fourier transform that allowed us to start with the Fourier transform and go back to the time domain, right? So how do we do that for Laplace transforms? So inverse Laplace transform. Now, if I was mean, I would have showed you the mathematically sophisticated way of doing this. How did we do the inverse Fourier transform? Analysis synthesis equation. It was an integral over omega, right? But now our variable in the Laplace transform is s. It's a complex thing, right? It's not just one variable omega. It's the real part of s sigma and the imaginary part, which is omega. 2 things, right? So it's a plane. So what am I really integrating, right? What would I really be integrating? We could do this, again, if I was mean. We would have to do what people call contour integrals on the complex plane. There's a way to do it that way. But we'll do it the more practical and easy way without going into much of complex analysis. Much of it is not needed for this course anyway. So we'll just use the cute little thing called the partial fraction expansion. That works for, more benign looking Laplace transforms. If your Laplace transform has the form of a rational function, polynomial by polynomial, then this will work. Okay? And you're not going to have to evaluate any integrals in the complex plane or anything like that. Okay. So how does that work? So I'm going to illustrate this. Why am I jumping from example 7 to 9? Goodness. Okay, sorry about this. Sorry about the pause. But my notes shouldn't go from example 7 to 9, should it? Okay. So, here I give you an x of s. It's an example. I'm not going to number. Who cares? X of s is 1 over s plus 1, s plus 2. So we did things like partial fraction expansion when we were actually doing also the inverse Fourier transforms, because the whole point there was to break apart something like this into a sum of simpler things, and those simpler things we knew immediately how to relate to the time domain, right? So that's what we want to do here. So I'm going to write it as some number a by s plus 1 plus another b s plus 2, right? And if I can find numbers a and b such that this equality holds, going back to the time domain will not be an issue, because you've already seen examples where we had things like 1 over s plus something, right? So we can just use those examples to go back, right? So how do I find a and b? We did variants of this in other examples in Fourier transform. So you just simplify this expression on the right and make it look like what's on the left. So the right gives you a plus bs, and then 2a plus b. Is that clear to everyone where this came from? Yes? No? I just gave them a common denominator. That means I multiplied the first term with s plus 2 both in the numerator and denominator. And I multiplied the second term with s plus 1 in the numerator and denominator. So that means a plus b should be equal to 0, because there is no s term on the left-hand side. And this should be 1. If you did this expansion in a good way, meaning that you were careful enough to represent each term, then when you're solving for a and b, you're not going to get any ill-conditioned or you're not going to get ill-posed cases where you don't have a solution or infinite domain. You're not going to get those. If you're getting something funny, that means you left something out here. Okay? We'll see the situation shortly where you have powers of terms, like not just s plus 1, but s plus 1 squared in the denominator. That will require a little more care. But for this type of thing, when the poles, negative 1, negative 2, are distinct, no repeated poles, then there's no problem. You just do it this way. So 2 equations and 2 unknowns. So 0. 2a plus b is 1. So that means that a has to be 1 and b has to be negative 1. All right, so now x is broken apart into simpler bite sizes. S plus 1, s plus 2, right? So what is x of t? E to the negative t minus e to the negative 2t times u of t, right? The answer is yes, maybe. Okay? That is a valid answer, but that all depends on what the region of region of convergence is, right? Because we saw that 2 things can give rise to this, for example. One of them was indeed e to the negative t u of t. That was example 1. But example 2 told us that there is yet another suspect who can give us this Laplace transform, and that is negative e to the negative t u of negative t, right? So the answer to the inverse Laplace transform is not unique unless I tell you what the region of convergence was, right? So the answer is what you just told me if the region of convergence is what? S greater than what? Greater than negative 2 and negative 1 as well, therefore greater than negative 1, right? Is that right? Okay, so if I told, so the message in this example is that I can't really ask you for the inverse Laplace transform unless I tell you what the region of convergence is. It's not a fair question because it's not a unique answer. Okay, there could be other answers to this, for example, such as like take this one for this, e to negative t, u of negative t, and for the other one, take what you told me, which is e to negative 2t, u of t. Right? Now, let's see, what would be the ROC for this? If that were the answer, what would be the ROC? So for the first one, you have to be smaller than negative 1, right? For this to come out, right? For this to come out, you need real part of S to be negative 2, right? Okay, so there is a narrow region of convergence for this answer. It's between negative 2 and negative 1. So it's a strip here. Anyway, so it went too wide. But anyway, so there's a short strip where this happens, right? I can take both of them to be left-sided. So that would be another answer. So that would be e to negative t, u of negative t, and positive e to negative 2t, u of negative t, right? Now, this would also reverse this term. So I would need real part of S to be less than negative 1, also less than negative 2. The more restrictive of the two is less than negative 2. Real part of S less than negative 2. So we actually have multiple answers if the ROC is not given. This is 1, this is 2, and it goes with this ROC here. And then this is answer 3. There is, in fact, a potential candidate for a fourth one, right? I could pair it differently. I could choose the left-sided signal from here and the right-sided signal from here. But the left-sided means real part of S has to be bigger than negative 1. Right-sided requires less than negative 2. There is no intersection of those two, right? So the fourth answer has ROC empty set, right? Therefore, it's not even an answer, so we're not going to write that down. Okay? Agreed? Is it clear what I said? So here they intersected, but in the fourth case, I'd be looking at the intersection of this and this, which doesn't exist. They don't intersect. So there's no fourth answer. Now, if I forget to give you the ROC, you should assume right-sided. Okay? I will try not to forget, but in typical applications, we'll be trying to solve differential equations for corresponding to causal systems, things that where the time flows in the right direction, from negative to positive. And in those cases, we'll be mostly dealing with right-sided signals. Okay? So your instinctive answer 1 is actually the default answer in this course. Okay? So good job with your instincts. All right. So, okay. What should I do next? All right. We're going to talk about some of the properties, but I'm not going to bore you to death with properties, so I'll just briefly mention some. For example, if I told you that if I have a signal x1 whose Laplace transform is capital X1, and I have another one with this Laplace transform what would you tell me about the Laplace transform of their sum, maybe scaled by two numbers a and b? It's linear. That's the linearity property. Simply because, we are applying an integral to these signals, right? We are multiplying them with e to the negative st and integrating. But we can split this over sums and factor out a and b. Therefore, it's linear. So I'm not going to spend any time. I've already spent too much, right? Any objections to this? No? We saw similar things in Fourier transform. Same idea. Linearity. Okay? The only difference now, this is L. So the cool thing about these properties is they aren't exactly new. At least when you substitute S equal to j omega, you should see a property that we already discussed, right? So if you want to have fun out of this discussion, that's one way to do it. Just look at whatever I'm writing, put S equal to j omega, ask yourself, do I recognize this property? Is this something I used in the exam, for example? So for example, one of the properties is the time shift property. Why did I call this one? Just linearity. Linearity. Time shift. Easy to prove, so easy that I'm not going to do it. If I have x of t giving me x of s, then x of t minus t naught will give me e to the negative st0 times x of s. Put s equals j omega, what do you see? It's the time shift property of Fourier transforms, right? Same thing. Of course it should follow, because Fourier is a special case of Laplace. Proof is simple. It's just a change of variables, not worth talking about. At least it's very similar to what we did in the Fourier transform case. Frequency shift. So what would I have to do in the time domain to get x of s minus s naught? Let's see if you can guess. Let me ask you the Fourier version of this. What would you have to do in the time domain to shift the spectrum to the right by omega naught? Multiply with e to the j negative j omega naught t, right? X of t. Yes, positive. Good, thanks. So, take a guess now for the Laplace transform. Wait, why negative? Positive S0, t x of t. So that's kind of cool, right? If you know the Laplace transform of any signal, that signal multiplied by any exponential signal, you don't need to do the Laplace transform again. Just shift s by the exponent. It's kind of useful. All right. You might ask, in some of these properties, what happens to the region of convergence, right? So when I gave you this, perhaps this was true when s is equal to r, the region of convergence of the original Laplace transform, right? So what do you think would happen here now? Take a guess again. What should I do with r, the original region of convergence? Let's say this was to the right of some line, okay? So what do you think will happen to that line? It will also move, right? So the new region of convergence will be the old set R plus S naught. Now, this is a funny notation, but it exists. I'm not the first one using this. So what is a set plus a number? What is a set in the complex plane plus a complex number? add number to every element of the set. That means basically shift the set, right? So if R was, say this. Let's say this is your R, right? Let's say this is 1, okay? R plus 2 is going to be the operation where you take any element, add 2 to it. That means everything in this set shifts to the right by 2. So if this was to start at 1, now it's going to start at 3. All right? So that's the idea here. So R plus 2 looks like this. It's a funny notation, you know, a set plus a number, but that really means you add that number to every element of the set. Therefore, the whole set shifts to the right by 2. To the right because 2 is a real number, and you move sideways, not vertically. All right? That seemed to cause some unrest. So you can. Yeah, that's a good question. Okay, very good question. Okay, so shifting by a real number plus a complex. Wait, let me be clear. So this was R plus 2, right? What happens if I shift by 2 plus j? I also move everything up by 1, right? But this is a whole strip. It never ends anyway, right? So if I shift it up, nothing changes. Still, it's the same strip, right? So really, you know, because the region of convergence in our examples are always strips, they are basically defined by the real part, not the imaginary part. So what really matters here is I could just as well write the real part of S0 here, right? Because shifting vertically doesn't change the set, since it has no bottom or top, right? It just goes from negative infinity to infinity. All right, that's the frequency shift. Time scaling. You'll recognize this. In fact, you won't need to stretch your imagination much because nothing really has changed. So if I look at x of at, where it is a number, the Laplace transform will be 1 over a x of s over a. And that's really identical to the property we had for Fourier transforms. Remember, j omega by a? It's the same thing. Just j omega is s. Okay, and what happens to the region of convergence? It now becomes ROC. It now gets multiplied by A. Okay, we're not going to go do the definition, the derivation of this here, but whatever the set R was, now you take every entry of that set, multiply it by A. This is different than shifting. Shifting was adding a number to every element. Now you're scaling every element by A. This includes, as a special case, negative numbers. So let's say I take A equal to negative 1. What does this property say in that case? X of negative t will give me the Laplace transform of, this is absolute value of A, so that won't change anything. And I'm going to get x of negative s. And ROC will be negative r. Negative r means you just flipped it, right? If it was a strip, then wherever it was starting, you just flipped it to the other side. So if it was right-sided, it's now going to look left-sided. So let's think of an example to illustrate this. What is a good example? Actually, one of the examples we had at the beginning should work. So if I have e to the negative at, that was one of the first examples, right? U of t, that gave me 1 over s plus a, and the ROC was when the real part exceeded negative a, right? So if I apply this to this, right, x of t is this, now x of negative t is e to the at u of negative t, right? And according to this result, that's just going to give us a Laplace transform, which is 1 over negative s plus a. And what happens to the region of convergence? Yeah, it's very unfortunate that I'm using a for both things, but yeah, okay. Let me make this b, okay? The next letter in the alphabet. B, B. All right, now you can tell me. Well, a is negative 1 in this case, right? We're applying this result with a equal to negative 1. So, has to be smaller than b. Okay? So it just changed the direction. If it was like this, if negative b was this, now smaller than that. Okay? All right. So, conjugation. We had properties like this for Fourier transform, so it's good to revisit them. Conjugation, not conjugates. So, x star of t, what will that give me? Let's actually do this. This is less obvious, but also easy to derive, right? That means I'm doing this integral. E to negative st dt, right? Can I write this as some things altogether starred? What would go in here? What would happen to the integral if I want to star everything? If I want to factor out the star, that is. X of t e to st, right? Yeah, so is that right? Or is it s star? So wait, let's be careful. What is e to the st star? E to the s is e to the sigma plus j omega, right? So I'm interested in the star of that. That times t, right? But that is e to the sigma t, which is real, times e to the j omega t. So we are starring this, right? So that means starring each component. Real part starred remains the same. And the imaginary part starred becomes negative j omega t, right? So, therefore, we get e to the sigma minus j omega t, which is, if this was s, this is s star t. Okay? We actually derived the useful property. E to the st star is e to the s star t. Okay? So, the negative sign stays, but I should put a star here. Do you agree? All right, so what is inside? Does that look like x of s? It does, except that in place of s, I have a star. So I have x of s star here, and then another star from here. So 2 stars. X star of S star, right? So it's kind of annoying, but you know, if in the special case of Fourier transform, that actually simplifies a lot. So x star of t, I said, gives me x of S star star. But if I substitute S equals j omega, what do I get here? What is j omega star? Minus j omega star. And that's exactly the property we had for Fourier transforms. All right. Okay. A couple of useful properties. One is very important, actually. This is, I might as well change the color here to red. Convolution property. Take a guess what this says. We did this, we beat this to death for Fourier transform, so I'm not going to give it too much airtime for Laplace transforms, but you should guess what the statement will be. So if I give you x1 that has Laplace transform big X1 and another signal x2, okay, what is the property? Convolution in time domain gives me multiplication x1 of s, x2 of s. Okay, very useful property. It deserves the red color. It's useful because, among other things, when we are trying to look for solutions of linear constant coefficient differential equations, which we can treat as LTI systems, this property will basically say, instead of dealing with homogeneous solution, particular solution, etc., it will just say, take the Laplace transform of your input, multiply it by the Laplace transform of the LTI system. That's the solution of the differential equation. In Laplace domain, you still have to go back. It's doable. Okay? So that's a useful property. And two other properties that are sort of useful, and that will be the end of these properties. I'm sure there are others, but I'm telling you the ones that really matter. When you take the derivative, actually I'm going to give you a little pop quiz here without grading you. So what is the Fourier transform of d by dt x of t? J omega x of j omega. All right. So this was the Fourier transform. Can you make a guess about the Laplace transform? S x of s, right? This is also very useful. So taking the derivative of a signal in time domain means multiplying its Laplace transform with s. Multiplication with s is derivative. Okay? Convolution is multiplication. Derivative is multiply with s. That's a cool example. So just to illustrate this. Okay, so x of t sine omega naught t, that was the underived example. Okay, I did the cosine. I said sine can be derived similarly, and the answer was omega naught by s squared plus omega naught squared, right? So let's now look at the derivative. Can you see anything here? Yes, you should be able to. Let me now look at dx dt here. What's the derivative of sine omega naught t times u of t? Okay. And from the property we just saw, this should have a Laplace transform of what? S omega naught by s squared plus omega naught squared, right? What if I scale this by 1 over omega 0, so this went away? The linearity of Laplace transform would tell you that this also cancels, right? They scale by the same number, right? So, and that's basically what we had, right? That was the other example we had. When we had cosine, it was s over s squared plus omega naught squared. In fact, you can derive one from the other one. Okay? Now, I remember a tricky question. At least at first it appears tricky. So, could I do it the other way, right? So, if I gave you... I like this example. I remember being confused about this when I was when I was taking the equivalent of this class. So, but I figured it out and I was happy. So I'll walk you through the same experience. So let's say I now start with cosine. U of t, right? And that gives me s by s squared plus omega naught square. And then I take the derivative, right? Taking the derivative, d by dt x of t is going to give me s squared by s squared plus omega naught square. I just multiply it with s, right? But what is the derivative here? Times u of t, right? Okay. But then I told you what the Laplace transform of this. It is omega 0 by s squared plus omega 0 squared. So you'll multiply by this, it will be omega naught squared, but it doesn't match up what's going on. No. I mean, omega naught squared versus s squared are completely different. It's not a sign error. Well, let's be careful about this d by dt. So, you know that u of t is a factor there, right? So it kills the signal before time equal to 0, and cosine at time equal to 0 is what? It is 1, right? So all of a sudden it jumps and then starts oscillating. So this is the signal we were talking about, right? So the derivative you gave me works sort of here on the right-hand side, but it doesn't account for that jump, right? So this discontinuity, right? To account for that derivative, you would have to, so basically dx dt is not really equal to this. At time equal to 0, it just fails, right? So the way to deal with this is to add an impulse to dx dt. Because if I integrate an impulse, I get a step, right? So you can so I won't work it out in complete detail, but you need to add here a delta of t, and then this will give you 1 minus omega 0, because delta gives us the Laplace transform of 1 by s squared plus omega naught square, and then you actually match those up. So I was actually staying clear of this issue in the example I gave you, because when I talk about sine is 0 at 0, so you don't get that jump. Okay, so you don't have that to worry about. But anyway, so this wasn't even in the notes, so I just improvised this. And what is more important is the following example, the following property. So differentiation in the Laplace domain. So if x of t gives me the differentiation property, so if x of t gives me x of s, what do you think will correspond to d by ds of x of s? This is actually a very simple question, because x of s, you know, is x of t to the negative s t dt. So if you take the derivative of this orange expression with respect to s, you'll actually see what time domain signal would give you that Laplace transform. What do you think is the derivative of this with respect to s? Minus t, right? Because I have e to the negative s t. If I take the derivative with respect to s, I'll get a factor of t. So minus t x of t e to the negative s t. So that still looks like a Laplace transform, except it is the Laplace transform of not x, but negative t times x of t. So that basically is the proof itself. Multiplying by time leads to differentiation of the Laplace transform and the sign reversal. All right, so kind of a useful example of this. It's useful because we use it in partial fraction expansions, and that's coming in 2 seconds. So we saw this Laplace transform pair, 1 over s plus a, right? So if I apply this property, minus t times e to the negative at ut will be the derivative of this with respect to s. d by ds of 1 over s plus a. And what is that? S plus a squared. Cool. And now let's just get rid of this negative sign here. So that means t times e to the negative at will give us 1 over s plus a squared. Right? I can do that again. And t squared times e to the negative at u of t will be again another derivative of this and a negative sign. And if you work out the details, you're going to get, this time when you take the derivative of this, there will be a factor of 2, right? Negative 2 actually, right? And the negatives will cancel, so it will be 2 over s plus a cubed. So if you do it one more time, you will accrue another 3 coming in. So u of t 6 by s plus a to the 4. So inductively you can conclude that if I do this n times, u of t, you'll get, guess what here? Something to do with n in the numerator. Should be n factorial. And s plus a power n plus 1. Okay? So that's the general expression. That's a useful thing to know. It's particularly useful when you're doing partial fraction expansions for Laplace transforms with repeated poles. Yes? Oh, I see. So, well, good question. So you're taking the derivative in that direction, I guess. It'd be a directional derivative. So wherever point you're at, draw a line from the origin to there in that direction. That's basically what it is, right? What I just said. Let me answer that next time because I don't want to say something incorrect. Okay. So where I'm going with this is, I also want to finish up what I want to do today, but we'll come back to that. So the partial fraction expansions we were talking about work fine when you don't have repeated poles. So, but what if I have something like this, s plus 1, s plus 2 squared? What can I do now, right? I can't just say a over s plus 1 plus b over s plus 1, s plus 2 squared. That's wishful thinking. Try that, okay? Try to match the two sides. It's not going to work because this will be, you're not going to be able to find a solution to that because you're missing an important term. You should also add c over s plus 2, right? So basically, if you have the second power, you need to account for both the second power in the expansion as well as the first power. If it's the third power, you have to account for third, second, one. Everything that comes below would also has to be in the partial fraction expansion. And now you have 3 unknowns. And you're going to get equations, 3 independent equations where that has a solution. Okay? So somehow in the notes I didn't call them ABC, but it is basically that. And if you match the terms, I'll leave that to you. It's my instructional resilience project today. Leave everything to you, all details you derive on your own. So, but basically you're going to get this. S plus 2 negative 1 plus s plus 2 squared. So clearly, you couldn't get away if you didn't include this term, because that term has to be there. You won't be able to recover it. Okay? So that's an important trick. But the nice thing is now when I see terms like this, I know what time functions they come from, right? This I already knew. Let's assume that we are looking for a right-sided signal for which this is the Laplace transform. Okay, so that means we have e to the negative t u of t for this, e to the negative 2t u of t, and what about that? T times e to the negative 2t times u of t. Everything is u of t basically, but you can factor u of t out. Okay? So this, therefore, this example served an important purpose because this is an important building block when we use partial fraction expansions, because we might very well get higher powers in the denominator, and we have to deal with those. Last question before I close. What can you say about just if I were to ask you to take a guess, what would you say the region of convergence is for all these derivatives for all these t times e to the negative at terms? So the region of convergence for this was real part of s bigger than negative a. What about this? It is the same. One way to think about this is, if I multiply this with e to the negative sigma t, and sigma is bigger than, beats out negative a, that's going to look like t to the n times still an exponential decaying function. That's the role of sigma, right? Even if a is negative, therefore e to the negative a t is growing, you can multiply with e to the sigma t, where sigma is negative enough that it makes it grow, converge to 0 again, right? So, but then what happens? So you have something exponentially decaying multiplied with t to the n. What's the result? What happens to t to the n times e to the negative epsilon t, even if epsilon is very small but positive? Who wins this struggle? T to the n wants to explode. E to the negative epsilon t wants to converge to 0. There's a disagreement. Who is more powerful? Exponential always wins. Polynomials are weak compared to exponentials. So this will go to 0. Even if epsilon is 0.0001, right? That even weakens the exponential, but still, when t gets large enough, it will be able to beat out the polynomial growth. Exponential always beats out polynomial. So therefore, the fact that I multiplied this by a polynomial means nothing in terms of convergence, right? So after a finite amount of time, it will act just like an exponentially decaying function. So the convergence will therefore depend on the exponential part, and nothing's going to change here. So the notes you will see on the last page, a summary of signals and their Laplace transforms. It's a useful table to stare at. And be ready for the next time, because it'd be good if you remember all of these things. Okay? I'm hoping to see you on Thursday. We are at the mercy of PG&E. Yeah, and our own resilience. Yes. All right, see you guys.